the familiar sweep of the planets. Yet its orbit lay almost along the same plane that the planets occupy, inclined at only about 5 degrees. That combination, retrograde motion but low inclination, felt statistically odd. It was as if a traveler arrived along a road parallel to ours, but going the other way. The geometry of that passage made some astronomers quiet with curiosity, because coincidences like that, if truly coincidental, are rare. If it were not coincidence, what else might the path be telling us? Further observations unfolded the stranger truths. At nearly 3 astronomical units from the Sun, at a distance where comets built in our own system usually slumber and preserve their ices, this visitor uncoiled as if waking. It released water vapor in massive amounts, when most familiar comets do nothing at all. Not just a slow drip, but a surge. The activity at 2.9 AU contradicted the expectations of ordinary cometary physics. Even more surprising, when scientists analyzed the gases in its coma, the ratio of carbon dioxide to water turned out to be exceptionally high. For every part of water, there were 8 parts of carbon dioxide. That 8-to-1 ratio is unlike anything seen in comets that formed in our cold backyard. Carbon dioxide dominated the chemistry of this strange halo of gas. The spectrum of light the object reflected told another story. It was not simply bright or dim, but it polarized light in ways that did not match known cometary behavior. Polarimetry, measuring the oscillations and directions of light waves, revealed anomalies. The patterns suggested unusual dust geometry, perhaps grains with internal structures or surfaces that scattered light in unfamiliar ways. The polarization signatures bore a negative extremity and phase angle changes that defied standard models. When faced with such data, astronomers do what they always do. They measure again. They cross-check instruments. They test for error. The anomaly persisted. And yet, one more disquieting paradox emerged. When large amounts of gas are expelled from a small body, physics dictates a recoil. Gas jets act like microscopic thrusters. Over time, they nudge an object off a purely gravity-determined orbit, producing measurable non-gravitational acceleration. This is well known and accounted for in cometary dynamics. But the non-gravitational acceleration measured for 3I Atlas was far weaker than the observed prodigious gas release should have produced. The magnitude of the gas flux suggested a stronger push. Instead, the object seemed stubbornly steadfast, barely perturbed. This mismatch created a tension between observations that demand explanation. On one side, large gas emissions, extreme CO2 dominance, odd polarimetric behavior, a retrograde, hyperbolic orbit with a low tilt. On the other, a weak, non-gravitational acceleration inconsistent with the scale of outgassing. If the outgassing were real at the observed scale, the body must be much more massive and thus larger than some estimates allowed. If it were massive, how could it have formed with such an unusual composition and surface behavior? If it were small, why was it not being accelerated? Estimates for the size of its nucleus varied wildly. Some analyses suggested a compact body, less than half a kilometer across. Others allowed for diameters, up to 5 or 6 kilometers. The difference between those numbers is not small. It changes mass and inertia by enormous factors and flips the calculations that follow. When scientists encounter such a thicket of contradictions, they must do what science exists to do: gather more data, broaden hypotheses, and be willing to consider uncomfortable possibilities. The most conservative approach is to imagine that 3I Atlas is an extreme yet natural variant of cometary physics. Perhaps it formed in a region of its parent system where volatiles other than water accrued preferentially. Certain formation environments could produce cores rich in carbon dioxide, with layered structures that release gases in unusual bursts. Perhaps the internal porosity or compactness is different, trapping or channeling gas in a way that changes the effective thrust. Perhaps rotational dynamics spread jets in directions that cancel net impulse. Each of these is plausible and can be folded into models, though with significant adjustments. A more daring line of thought moves into deeper waters. Some researchers whispered of a black swan event in astronomy, an occurrence so rare and consequential that it forces the revision of assumptions and frameworks. The term black swan had traveled into astrophysical discourse because sometimes unpredicted anomalies have reshaped how we think about the natural world. Could 3I Atlas be such a moment, nudging us toward new understandings of material behavior, of small body dynamics, or perhaps even of physical law at particular scales and configurations? This is not to suggest headline-grabbing claims about broken gravity or overturned relativity. Science does not leap to such conclusions lightly. Instead, the suggestion is more measured. Maybe there are processes, combinations of microstructural geometry, phase change dynamics, and radiative interactions that are not yet captured by our current models. Maybe on the surface of 3I Atlas, microscopic layering, exotic ice phases, or mineral coatings produce behaviors that defy the simplified assumptions built upon solar system observations. Or perhaps there are kinds of feedback between surface chemistry and gas release that, under particular conditions, create near cancellations of thrust on macroscopic scales. These ideas remain speculative until they are tested. But they are worth considering because the alternative, ignoring the mismatch, would be to stagnate. Meanwhile, the human side of this story plays out with a mix of methodical diligence and restrained imagination. Observatories across the globe trained instruments on the visitor. Radio telescopes listened for molecular lines. Infrared arrays mapped thermal signatures. Polarimeters tracked the strange polarization. Teams coordinated observation schedules in near real time, aware that the window for meaningful data would not last forever. In the quiet nights of observatories, technicians adjusted filters and recalibrated detectors. Graduate students wrote scripts to sift terabytes of data. Senior scientists organized teleconferences at odd hours. It was, in many ways, a classic example of how modern science answers the call of a rare phenomenon, with cooperation, redundancy, and patience. At the same time, communities of amateur observers contributed images and time series that filled the gaps between professional facilities. Citizen science platforms aggregated visual confirmations and photometric data. Each new spectrum and photometric curve fed into global databases. Models were adjusted, then tested. Some parameters tightened, others remained obstinately uncertain. Uncertainty here was not a failure. It was the currency of honest knowledge. Public communication became a tightrope. In a world where every unusual astronomical headline can be amplified into sensational claims, scientists and communicators worked carefully to distinguish robust results from preliminary speculation. The press wanted stories, and the public wanted wonder. Both were valid, but fidelity to nuance was essential. Researchers were cautious to say what the data truly supported. Anomalies were present, they were significant, and they invited deeper study. Beyond that, the community avoided leaps. Speculation about black swan scenarios was framed as a useful intellectual exercise, not as a declaration of revolutionary physics. Within the labs and online forums, different narratives emerged, like competing constellations in a dark sky. They pointed to known chemical processes and proposed that the CO2 dominance could be a formative signature, reflecting a birthplace with different temperature histories and volatile reservoirs? If so, then 3I Atlas is a message about diversity. Planetary systems can produce bodies with substantially different volatile budgets, and our models must be flexible enough to embrace them. Others focused on morphology. If the nucleus were highly structured, with massive subsurface cavities, or an asymmetric distribution of volatiles, the outflow could be more complex than a simple rocket effect. Jets could be balanced by counterjets, or the geometry of mass loss could distribute momentum in ways that net to small acceleration. Laboratory experiments and computational models began to explore three-dimensional porosity and jet dynamics at scales relevant to cometary nuclei. These endeavors required time, but they also yielded insights that could be applied to future encounters. Then there were the theorists who considered more exotic but testable physics. They did not stake their reputations on overturning pillars, but they examined whether known laws might permit subtle, scale-dependent effects under unusual compositional or structural regimes. They asked if phase changes involving clathrate ices or complex organics could lead to delayed or buffered outgassing. They calculated whether radiative torques or photophoretic effects could conspire to counteract the direct momentum transferred by jets. These models were complex, layered, and, crucially, falsifiable. That made them worthy of attention. All hypotheses required better constraints on basic numbers. The wildly varying estimates of nucleus size were a particular problem. A 5-kilometer core and a 300-meter core imply orders of magnitude difference in mass, and therefore in how the object would respond to any thrust. Pinning down size required clever analysis. Combining thermal emission measurements, limits from brightness, scattering properties from polarimetry, and dynamical fits that accounted for possible non-gravitational forces. It was painstaking work, and it highlighted how a single parameter of uncertainty can ripple outward into many interpretive paths. As people around the world looked up, small human stories accumulated like stardust. Teachers used the anomaly as a lesson in science clubs. Poets wrote short lines about an ancient messenger slipping silent through the night. Children asked questions that prompted simple, honest answers. Why does space have different kinds of comets? Could something like this happen again? The emotional resonance was gentle too. There was a shared sense of being part of a living inquiry. The public learned how science contends with surprises by being systematic, skeptical, and open to revision. In the end, 3I Atlas may turn out to be a deeply instructive oddity that teaches us about the diversity of planetary systems. It may be a case study in how early formative environments shape volatile inventory and microstructure. Or, in time, it could expose processes that require extensions to our current models. Whatever the final verdict, the encounter is already valuable. It has focused attention on the need for rapid, coordinated observation strategies for fleeting interstellar visitors. It has highlighted the importance of cross-disciplinary work, combining observational astronomy with laboratory astrophysics, advanced modeling, and comparative planetology. There is a quiet lesson in the way this story unfolded. The universe does not owe us simplicity. It may occasionally present us with an object that resists tidy categorization, demanding patience and humility. That resistance, strangely, is not an obstacle to wonder. It is the engine of knowledge. When an anomaly appears, the right response is not to rush to conclusions, but to widen the aperture of inquiry, to bring more eyes to the sky, and to sharpen our instruments and our questions. So as you allow sleep to come, picture 3I Atlas sliding further into the velvet of interstellar space. Imagine it as an ancient traveler that carries within its frozen heart the chemical memory of another star. It moves forward, indifferent to our theories, but intimately entangled with our curiosity. We will continue to watch, to measure, to calculate, and to wonder. We will return to its story as more data come in. And with every new piece of evidence, our map of the cosmos becomes a little more elaborate and a little more true. Breathe in, breathe out. Allow the questions to rest for the night. Remember that uncertainty is part of the beauty of science. It is the seed of future certainty, the quiet engine that pulls us gently forward. Tonight, in the shadows under the same sky where an interstellar wanderer once sped by, you are connected to a long chain of observers. Those who listen, those who measure, and those who imagine. Good night, dreamer. Good night, bedtime universe. Until the next story, may curiosity lightly guide your sleep. Hello, dreamers, and welcome back to Bedtime Universe. Before we begin, take a gentle breath. Let the cadence of your breathing find an easy, slow rhythm. If you like, tell me where you are watching from and what hour it is where you sit. No matter the place or the time, you are here now, and tonight we will travel together into a quiet pocket of the cosmos, where one small visitor changed how we listen. This is the story of 3I, Atlas, an interstellar wanderer whose passage through our sky felt at first like a whisper, then like a question. It is a tale of precise measurements and patient nights in observatories. It is also a story about how the unexpected can nudge a whole community of scientists toward new ways of seeing. We will move slowly, with the gentleness of someone tracing constellations with a fingertip. We will follow the object's path, the data it left behind, and the ripple of curiosity that spread from observatory to observatory. There will be technical moments, and there will be quiet ones. Both are part of the same night. The discovery was simple, at least in its beginning. On July 1st, 2025, a telescope in Chile called Atlas tagged something faint and moving. The pipeline flagged an object that did not belong to the known catalogue. The orbital calculations converged on an eccentricity far greater than 1, near 6.1 to 6.2. That number was a mathematical announcement. This object was not bound to our Sunday. It was passing through with a speed of nearly 60 kilometers per second. In a universe where many things circle patiently, for a while the world treated it like the other two interstellar guests we had seen before. But even early on, there were strange notes in the score. James Webb, peering with its deep sensitivity, recorded spectra of its coma. The composition was not dominated by water vapor, as is typical for comets formed in the cold outskirts of our system. Instead, the signature was unmistakably strong for carbon dioxide. That chemical voice suggested a birth environment unlike ours. The visitor was not merely alien by origin, it was alien in the way it held heat and released breath. The weeks unfolded like a slow experiment. In early October, on the 3rd, the object paid a close call to Mars. Radio and optical tracking from spacecraft and ground stations confirmed that it was exactly where the orbital predictions put it. The trajectory calculated from those data matched the predicted path with an almost unsettling steadiness. Then the geometry of the system shifted. From our vantage, the object moved behind the Sun in superior conjunction, an interval when direct optical observation becomes impossible for a time. Astronomers call it a blind spot. During that conjunction, the Sun itself became unusually active. On its far side, energetic events erupted. 3 major coronal mass ejections, launched in sequences